Alright, hi. So this is episode 1 of a layman's look at climate change. Today I'm going to talk about why is the Earth, is the Earth getting hotter, and where is the heat coming from? What you can see here is that the Earth is heated by the sun. Okay, and so the heat is coming in from the sun, which is very hot, hits the surface of the Earth, and then the Earth is sending heat out into space. So during the day, the sun is heating one particular side of the Earth. Okay, and then the other side could just be losing heat. But even the side that's being heated from the sun is also losing heat the same way that the other side would. It's just that it's balancing out so that there's more heat coming in on that side than the heat that it's losing, and so the day slowly heats up, and then as it becomes night, well, you start to lose some of the heat. And so the Earth is, even though the temperature is going to change during the day, there's going to be an average temperature over the day that depends on how fast the heat comes in and how fast the heat goes out. There's a few mechanisms that you would have learned about in school about how heat can be transferred. So they're called conduction, convection, and radiation. So conduction just means if two things physically touch, and one is hot and one is cold, so your hand touches the bench, your hand's warmer than the bench, then your hand will get slightly colder and the bench will get slightly warmer just because of the movement of the atoms in your hand. So the heat is going from the hot thing to the cold thing. Convection, you might remember the little tea leaf experiment. Okay, so the hot thing's moving into different parts of the cup. And radiation, well, we know that there's no matter between the sun and the earth. The space is a vacuum. But by electromagnetic radiation, heat is able to come from the sun to the earth. And so it's also possible for the earth to lose heat by radiation. So the question is, what would happen if the heat coming in was different from the heat going out? So if there was less heat coming in than going out, then the Earth would get colder. If there was more heat coming in than going out, the Earth would get warmer. But would the Earth keep getting warmer forever? Well, what actually happens is that as the Earth gets warmer, something changes. The warmer something is, the faster that it can lose heat. So the Earth would start getting warmer if there was more heat coming in than going out, but then it would get to a point which would be like a new equilibrium, a new normal for the Earth, where, okay, now that the Earth is hotter, it's able to lose heat as fast as it's gaining it, whereas the heat coming in from the sun hasn't changed, so then it'll be balanced. Heat in equals heat out. Okay, so that's not the only factor, though, that influences how quickly heat transfers. Okay, there are two things. Okay, the temperature difference between the two things, so between the Earth and space or whatever, and how efficiently the materials can transfer heat. So let's go back to the example of you're in a room, okay, say you're in your kitchen, and the temperature in the room is 20°, and the temperature inside your body is 37°. If you put your hand out into the air, then your hand won't feel very cold. If you put your hand on the bench, your hand will feel colder. And that's not because the bench is any colder than the air, it's just that the bench is made of a different material and the heat is able to transfer faster from your hand into the bench than from your hand into the air. So what we're concerned about is not just the total amount of heat transferred or the temperature difference, but how quickly the heat can go into or out of something. And this second thing, the efficiency, has got a scientific name. I think it's the heat capacity. Okay, but like I said before, we're talking about different mechanisms of heat transfer, so it's not completely exact here, but these are the two basic principles. Okay, the rate the Earth loses heat will depend on the temperature difference between it and space, and secondly, the materials. So we'll come back to this. Let's have a look at this diagram here that shows what I mean by the temperature difference. So having a look on the right here, there's a picture of someone in bed and their body is 37°. When they're in bed in the summer, the air outside is 20 C, which is 17 colder than their body. When they're in bed in winter, the air outside might be 0 C, which is 37 colder than their body. So here we have a greater temperature difference in summer as in winter, okay, because even though the body stays the same, the air outside changes. If we look on the left side of the diagram at the Earth, it's a different situation. Space is always close to absolute zero because it's a vacuum, so it's 0 Kelvin, which is about minus 273 C. The Earth has an average surface temperature of about 15 C, which is 288 Kelvin. But let's say that after global warming happens, the Earth has a new equilibrium temperature of 4 degrees hotter, so now it's 232. So now you can see the temperature difference is greater between the Earth and space, not because space got any colder, but because the Earth got hotter. So we only care about the temperature difference, not which one is getting hotter or colder. Okay, so what can you do in winter if you don't want to lose heat faster than you do in summer? Well, we said that the other thing we can change is the materials. So in winter, you might wear a warm blanket. And the point of the blanket is that the body doesn't lose heat as fast. So your body would be losing heat faster because the air outside is colder, but you're cancelling that out by saying that you don't lose it as fast because the blanket you're wearing is thicker, and that prevents the heat from leaving your body quickly, which means that the heating engine inside your body has more time to reheat, to restore the heat that you would be losing to the outside air. Whereas in summer, you don't want to wear the thick blanket because you're not losing heat that fast. So if you slow down the rate of heat loss even more by wearing a thick blanket, then your body might start to feel uncomfortably hot. So you'll wear a thinner blanket. Okay, so we have the same thing with the Earth. We said that the heat coming in from the sun has to be cancelled out by the heat going out from the Earth. Okay, so if the Earth can efficiently lose heat, then that means that it doesn't have to be at a very high temperature compared to space. Okay, but if for some reason the Earth wasn't able to as efficiently lose heat, then that means the heat coming in would be more than the heat going out. The Earth would get hotter until it reached a new stable temperature where now, even though the Earth is wearing a warm blanket, so to speak, the heat going out would still equal the heat coming in. And in the next episode, I'm going to say, all right, so the Earth gets hotter, the Earth doesn't care, but what does it mean for the things actually living on the Earth? But before I finish up, let me just talk a bit about what the blanket is around the Earth. So what's stopping or what's affecting the rate at which the heat leaves the Earth? Okay, and the answer is the atmosphere. So the air, all right, obviously we breathe air, 70% nitrogen and something like 20% oxygen, and it's got some other atoms, it's a gas. Okay, but why doesn't the air around the Earth just fly off into space? Well, air still has a weight, so it's got mass. So the gravity of the Earth does sort of keep the air around the Earth, although it gets thinner the further you go up into space, 50 or 60 kilometers up. Okay, but that air, and I guess the composition of the air, the atoms in the air might change as you go up. But that air is basically what's insulating the heat on the Earth. One thing I didn't mention is geothermal energy. So just to go back a bit, okay, the heat coming in, maybe it could be absorbed into the center of the Earth and then maybe not released for millions of years. But on the other hand, the center of the Earth is actually hotter than the surface, and sometimes you get hot springs which are heated by the center of the Earth. So if anything, the heat inside the Earth is contributing to the amount of heat that we have to lose. But either way, it's negligible compared to the two things I spoke about before, the heat coming in from the sun and the heat going out into space. So with the moon's day is much longer than ours. The moon's day lasts 13 days, and then its night lasts for about 13 nights. So the sun heats up one side of the moon, and that side gets very hot. And then the other side of the moon gets very cold. But the average temperature on the moon is less than it is on Earth. Now, the amount of heat coming into the moon is the same as the Earth or like per square kilometre. So when we adjust for the difference in surface area, okay, the moon is about the same distance from the sun, so the heat in is similar to the heat in on the Earth. Okay, but the moon can lose heat much easier, especially during its night. I mean, during its day, it can be over 100 C there, but that's because it's constantly being bombarded by the rays of the sun. Okay, but the difference between the Earth and the Moon is just that, well, they've got a different atmosphere. Okay, the Moon, there's not really as much of a layer of gas around the outside, and so the Moon can lose heat into space very quickly during the night. Okay, and the Earth doesn't. So later on, we're going to look at what specific features of the atmosphere, okay, are causing the Earth to not be able to lose heat as quickly, which is why the Earth might have to become hotter in order to be able to reach an equilibrium temperature. Thanks. See you next time.